Hello, everyone. So I'll be presenting some of the exciting work that we have been doing on the AI testbeds at ALCF. My name is Murali Emani. I'm a computer scientist at the data science group. So we are exploring how the new or the novel AI systems can help run our scientific machine learning applications. So that's kind of your talk is all about. So quick intro. So we all know that there's a surge of AI and machine learning as such in the science applications. So they help to getting the science codes run better or do new additional experiments. So for example, the use cases are AI models can help in replacing any expensive simulations, or they can also use some data-driven models to build some more without any simulations. It also helps to in co-design of the experiments. So when we see this a tight integration between the AI and the science code, so we need to have an infrastructure that will help to accelerate these components within the applications. So we see that some situation where we have this experimental facility and there's a computing facility. So traditionally we run these large simulations on our supercomputers, and we have these AI accelerators. So they work in coupled with the traditional supercomputers, and those accelerators could be disaggregated or they can be combined together. So there's a lot of exciting directions that can be taken going forward. So we started this, the AI testbed at ALCF. So our primary goal is to understand how this infrastructure of the next generation hardware performs. So we want to test their usability and efficiency across a wide variety of models and how we can use them for the science codes. And this is a platform where we have folks who are trying out the systems, for example, on the traditional supercomputers, which use maybe the NVIDIA A100s. Now they want to try what happens if I'm using an AI accelerator to test my model. And we're also using this as one of the workplaces to understand designing the next supercomputers. How can we integrate these AI systems into the traditional ones to accelerate science? So currently in the AI testbed, so we have these 5 systems. So you have Cerebrus CS2, the Sambanova Datascale SN30, there's a GraphCore Bauport 64, there's a GrokRack, and Habana Gaudi 1. Again, we started off with the first generation of machines for majority of those. And from our preliminary investigations, we found they are pretty exciting. So next we have the next generation of those machines deployed, and also we increased the scale of the systems. So currently the Cerebrus, we have like 2 CS2 engines, and each has 850K code. It's a massive compute wafer. It's primarily targeted for compute intensive workloads. For this Sambanova Datascale, so it's characterized by a larger memory availability, and we have like 8 nodes of the SN30s. The GraphCore Bauport 64, we have 4 nodes. And the equivalent is as an IPU. It's kind of mainly targeting for irregular workloads. GrokRack is primarily aimed for accelerating the inference jobs. And even we recently are upgraded to next generation machine as well. Habana, so we are looking at exploring the Gaudi 1 and also the Gaudi 2 systems. So what we're doing today is, so I'll be presenting a brief overview of these systems and some of our experimental evaluations and use cases that we are working on. And later in the afternoon session, so we have the dedicated hands-on, like where we work on some of the sample scripts that you can try for the 3 machines, the Sambanova, GraphCore, and Cerebrus CS2. So we have Sid and Varani from our team who will help us with this hands-on session. So, so again, we also have a director's discretionary program where now, if you see this as an exciting work that you want to explore for your applications, you can always apply for a DD allocation request, and you can get the allocation on any of these systems. for a longer period of time, so you can just help or try running your models there. So right now we have the CS2, the SN30, and the Part 64 are available for the DD allocation program. Also, we have good community engagement. So we have dedicated training workshops working closely with the vendors for all the systems. And again, we are having some tutorials at major venues like supercomputing. So we had one last year. So we're also organizing one tutorial at SE this year. So we're understanding, so how are these systems different from, say, the traditional, for example, GPUs? So this is a snapshot of the data flow architecture from the Samba Nova. So on the top, you see there is a simple convolution graph. There are different layers, the convolution layers and their weights. And so that's a very simple model. So on the left-hand side, you see there's the traditional way that we launch these kernels is on a kernel by kernel basis. So there are some optimizations that you can do. But this approach is kind of has some restrictions on it's bottlenecked by there's a memory bandwidth, there's some kernel launch overheads. On the right side, if you see there's the data flow way. That's how the Samba Nova implements it. The goal is to eliminate the memory traffic and any associated overhead with that. So we see this is a spatial mapping. So there's all the compute units within the RDU, and all the layers we see on the top level. So they're all spatially mapped onto these chips. So when the kernels are mapped, so the data flows on chip between these, and it helps in reducing the memory traffic. So the core compute unit of the Samba Nova system is called a reconfigurable data flow unit. That's the RDU. And like I said, this is a SN30, which is the latest generation of the system. So earlier we had SN10. So the RDU, so there are some specs that I'm listing here. So if we go down a little bit deeper, so each RDU is composed of tiles. So there are 8 tiles, and each of them have the units called as for compute and memory. So they're called as pattern compute units, PCUs, and pattern memory units as PMUs. And again, there are additional units for for the addressing or the coalescing units for setting up the communication as well. Again, the granularity is that multiple kernels can launch on this, and there's the number of tiles that can be used can also be varied based on the kernel and its behavior. And there's a direct access to a massive off-chip memory, and each RDU has around 1 terabyte of memory with that. So it's pretty a lot of capacity out there. So again, as I said, so each tile is composed of a network of PCUs and PMUs, and the compiler, it implements how the kernels from a code are mapped onto these PCUs and PMUs, and they are executed in using the data flow pipeline. Now we saw that's the single unit, that's an RDU. Now we look at the next version, the scaling version of that, so the SN30. It's a single node, and this is combination of the data flow efficiency in implementing the mapping of the kernels to the units, and again there's a large memory capacity, so they're all coupled together. So the SN30, so that's a node here. So we have 8 SN30 RDs within them, and there's 8 terabytes of total memory available here. So in terms of the software stack, so we have this Samba flow that's used for taking any model and enabling that to run on the SN30 system. So again, it's works over PyTorch API. I get the Samba flow. There's a separate compilation path where it does the the mapping on the PCUs, PMUs, and it generates a file called a SPEF file. And there's a Samba runtime, which actually does this offloading and mapping on across CPUs and RDUs, and that's how it implements the kernel. So as I said, in our AI test bed, so this is a configuration that we have 4 racks of these machines. So there are total 8 nodes. And again, each node has 8 SN30 RDUs. So totally we have 64 available RDUs. And is the notation that we have like SN30, R1, H1, all the way there. So we'll learn more of these in the afternoon session as well. Next, moving to the Cerebrus system. So the Cerebrus system, the core unit is called as a wafer scale engine. Now you see that it's a pretty big chip compared to what you used to see that. And each chip or the wafer scale engine has 850K cores, the compute cores. So it's very massive compute capacity that's available. And you see that again, there are some other specs in terms of the transistors, the chip, and the memory bandwidth as well. Now, next we move to something called as a wafer scale cluster. Now we have seen a single wafer scale engine. Now we are moving to a wafer scale cluster. So this is the Cerebrus wafer scale cluster that we have. So there's a dedicated nodes for pre-processing the streaming of the training data. And then again, there are nodes for the MemoryX and SwarmX. So MemoryX is primarily used for storing and streaming the model weights. And SwarmX is primarily used for broadcasting those weights across the different CS2s. So basically it helps to scale running across multiple CS2s. And next we have the actual CS2 engines where the actual training happens. So at our end, so we have 2 CS2 appliances and the 16 worker nodes. There are again the 24 MemoryX and SwarmX, 6 SwarmX nodes. So so based on this topology, so how is our kernels or our jobs run on the CS2 cluster? So that's using a technique called as weight streaming method. So weight streaming method is, so the core compute happens on the wafer scale engine on the CS2. But the weights are stored and they're streamed from the external model memory. So on a layer by layer basis, the weights are streamed, the compute happens on the engine, and they're again streamed back. So it kind of helps in decoupling the compute and memory, and that's how it enables to run efficiently. So next, moving to the graph core system. So the graph core BAW part 64. So the core unit here is called as an IPU. That's the intelligence processing unit. So here we see a high-level pictorial representation of, say, the CPU, GPU versus IPU. So if you look at, say, GPU versus IPU, so IPU is aimed for or works in like a MIMD fashion. So there's massively parallel implementation occurring also at the hardware level. And in terms of memory, again, there is large distributed SRAM that's available per IPU. And that helps in running those models where you need faster access to the memory as such. So going down a little into detail, so this is the BAW IPU. So again, we have something called as the IPU tiles, and each IPU tiles has again certain number of processing cores with those. And again, each IPU has again associated memory within them, so they're all tightly coupled. Now there's a IPU exchange, so that helps in the communication between all the available IPUs. And now how do we scale across devices? So we have, so this picture is showing within a single, how can you scale multiple IPUs? Again, there's something called as a dedicated IPU link, which provides a high IPU to IPU bandwidth, and that helps in running any distributed jobs and improving the bandwidth out there. So again, when we look at scaling across systems, so now we have each of those the IPUs before that we have seen, and now we again scaling them across multiple nodes. So it kind of helps in a modular design, and the kind of built with a very powerful the IPU exchange and also the IPO link for the communications. Again, I'm giving a very high-level overview. Again, maybe you can go through the slides with all the detailed information. So this is a snapshot of the BAO 2000, which is a kind of a building block for the large pod. So we have pod 16, pod 64. So BAO 2000 is the core of that. So each BAO 2000 has 4 IPUs. And again, it has around 3 gigs of in-processor memory. Again, you have support for streaming memory from the DRAM as well. So in the BAO pod 64 in the AI testbed, again, we have this 4 nodes, and that totals to around 64 IPUs, and they're noted as like GC Poplar 01 through 04. So in terms of the software stack, so the main software enabler is using the Poplar library. Again, it supports from different front ends, and again, the optimizations are taken care of by the software stack, that's the Poplar, and kind of doing all the implementation optimizations and kind of doing the mapping onto the underlying IPUs. So again, this is a very high level summary of the hardware characteristics of each of the systems that we have. So I'll just quickly note that, okay, if you see the compute unit, so there's a wide difference between what's the available compute capacity across these systems. And again, in terms of the memory, again, so again, you see there's a huge difference again across these different platforms. Now, given this diverse characteristics of each of the systems, so the main challenge is understanding how are these systems performing for different applications and what are their unique capabilities. So we did some studies out there. Maybe I'll quickly go to that. So last year we had done this benchmarking study on using a diverse set of deep learning models, going all the way from the primitives, which are the core kernels, like the convolutions and gems, to standard benchmarks like UNet, BERT, large, and again, few applications like UNO and Bragg-NN. Again, these were run on the first generation of the machines that we had last year. And more recently, we have also done some work on doing this comparative study of the large language models. Again, looking at the transformer block, which is a core block of any model, a GPT-2, and a GenSLM science application. So I know there's the paper that I've listed here, it has all the details, but I'll quickly go through some important examples. So here we are showing the UNet 2D example. On the x-axis, we are looking at 2 different batch sizes, and again, we are scaling across the number of devices from 1 through 8. Again, we are comparing the throughput. So if we see the highlighted ones, for example, for a batch size of 32, so the comparison is across the 8 A100s. Again, A100s, we are using them out of the box. And again, these runs were made on the previous generation system. So we see that across the SN10, the CS2, and the graph core systems, we see there's a huge improvement in the throughput when we are comparing to an equivalent run on 8 A100s. Now, again, looking at the scaling efficiency when we are increasing from 1 through 8 devices, again, CS2 has only 1, but for the A100s, SN30, and the graph core system, so we see there's a scaling efficiency is okay, but we are looking at more optimizations that can be done better. So this is for the unit example. Again, there are more studies that we did as part of that exercise. So I'll quickly turn over to the recent work that we have done is comparing evaluating the GPT model performance. So again, on the x-axis here, we are seeing the number of devices. On the y-axis, we are plotting on the throughput. So we're comparing the SN30 Gaudi 2, pod 64, A100, CS2, and again, AMD MI250s. So for this study, so we use the GPT-2 XL 1.5 billion parameter model for this study. And we try to be kind of getting using the same configurations as much as we can. So we're kind of fixing the sequence length, but again, the batch sizes were kind of tuned to that specific configuration and specific platform. So one of the key takeaway here is that, like, if you were to run on this model, say on the 64 A100, so the performance that we see on that scale, so we are getting that from just 2 CS2s or 16 IPUs or 16 SN30 RDUs. So what is this as even for the models that we are kind of seeing, the AI accelerators are seeing a better throughput performance across the number of devices. And again, the scaling efficiencies were also from all the way from 78 to almost like 100% scaling. So this is a snapshot. So we are trying to understand, like, now we have this massive compute and memory available on the system. So what happens if we increase the sequence length? Because that's kind of important when we want to have larger model with more generation capacity. So this is one study that we did on the 1.5 and the 13 billion parameter models, and we are trying to understand what's the impact of the increased sequence length on the throughput. So we see that on the scale of the devices, say 1 CS2 and 8 SN30, so we can have a much larger sequences that are currently supported. And so this proves that there's a lot of potential, a lot of capacity on these systems to run large models too. And again, each of these systems have run again like larger models, say the 175 billion parameter model as such. But for this study, we just started with the smaller variant of the GPT version. So next, we're trying to understand, these are for the standard models as such. Now, what's important is for the AI for science applications. So that's where our key focus is on. We have a lot of applications that are ported onto these systems, and we also did some study out there. Like there's an application which focuses on cancer drug response prediction. There's the protein folding example, and again there is a genome scale language models. That's a GenSLM. So the GenSLM model is a kind of the foundation model that we had. The goal of this application is for understanding what the behavior of the SARS-CoV-2 virus variant, and figuring out what are the mutations that can happen, the variants of concern. And again, this is looking at the gene level, but again, this can also be extended for protein. So I think there's a lot of further explorations that can be made, but this is the first step towards there. So here we're using the LLMs to understand this evolution. So there are these pre-trained models from 25 million all the way to 25 billion parameter models on the raw nucleotides. And this study, so we've done on the A100 GPUs, the CS2 and the SN30. So the GenSLM paper was also the winner of the ACM Gordon Bell Prize for HPC-based COVID-19 research last year, SC. So it's a very high-level snapshot of what's the model doing, but I'd like to focus on the right side. So there's this foundation models at different scales and different sequence lengths. And some of the scaling challenges are really important because the model is getting complex with given the increase in the number of parameters and also the sequence length. And when we look at like running them on Polaris or the A100 GPUs as such, so there are some limitations that can happen. So we want to figure out if we are running them on the CS2 or SN30, how are these systems performing for the GenSLM. So here is we are running this GenSLM on the Cerebrus CS2. So this can support up to a sequence length of 10K. And again, if you look at the tables here, it's supposed results for two examples, that's 123 million, 1.3 billion. And if you look at the plot here, so we also look at the scaling, right? The number of devices. So when we increase from 1 to 16 CS2, so we also see there's a kind of linear scale up that's possible on these large models. So on the SN30s, so these are some preliminary results. Again, there's more recent versions that we had. So this plot is showing like for the 13 billion parameter model and looking at 1K sequence length. You're looking at a scale for the SN30 RDUs and also the A100 GPUs. And if you look at those plots, so we see there's a near or linear scaling that we are observing on this. And with the recent optimizations, we also seen almost like 10 to 15x improvement with the new software optimizations. And again, there's a fine tuning and pre-tuning as opposed with the larger sequence lengths. So I've just listed one example for the science use case, but there are a lot more. So some of the key observations from our exercises is that the AI systems that we have, like they have shown a good scope for improvement, especially with say like traditional models or some of the science-based models as such. And because of their unique capacities, maybe the larger computer, the larger memory, so they cater to support say models with complex, higher number of parameters, or they can work with larger resolution data, and also they can be scaled to multi-chip systems. Again, however, there are some challenges in realizing this. So some of them are the porting efforts, because each system has their own software stack. So there'll be some refactoring or some changes have to be made from the existing codes. So that needs some effort out there. And in terms of the compilation times, what we observed was the compilation times usually tend to be longer. But again, we are looking at some progress, significant progress happening out there. We are trying to reduce the compilation time. So the other challenge would be the coverage of the different operators. So maybe not all operators are supported at this point. So based on the use case that we have, they're also increasing the operations that can be supported on these systems. And again, each of the systems have their own tools to do some performance profiling as such, and to understand the performance of these models, how they're running on the system, what are the utilization numbers, and that can help to optimize the code better. Now again, the other interesting trend is like support for the low-level HPC kernels. So these are the non-AI, the traditional HPC kernels. And again, there has been some work on this front. So there's some limited support at this point. We are trying to porting say many kernels on this on few systems. But again, this project is significantly seeing more improvement as we speak. So some of the efforts that we're currently doing is, so we are first focus is to have more science projects or applications run on these systems and leverage their unique capacities. And again, we're also talking or engaging with other AI accelerator vendors to understand their behavior and can we incorporate them in our testbed. And the other aspect is like how can we integrate these Axel or systems with the schedule such as PBS Pro, so it helps in effective scheduling of jobs across these multiple accelerators. And like I said, we're also trying to understand how we can integrate these systems to maybe the upcoming supercomputers. So that would be a very interesting work going forward. There's a lot of potential out there. So I'm listing some of the recent publications from systems on the AI testbed. And yeah, so that's all I had for today. Again, I'll be here. We have our team as well, so we can talk to us with any questions. And again, quickly going back to the agenda, we have the slot from 2:30 to 5 p.m. This afternoon. We'll be going through the three systems, the Sambanova, GraphCore, and Cerebrus. So we'll show you like how do you log on to each of the system, where to find the scripts, and how do you run some sample codes. And again, feel free to just try out, get your hands on the system, and we can work together on that. Again, there's a dedicated Slack channel if you have any questions, so we can also answer those questions in Slack. And I hope this session will be useful as a first hands-on on these AI systems. Like I said, there's again the DD allocation program. If you need a larger allocation on these three systems, we can definitely do that. So the request is you can be made in the ALCF website. It's only, I think it asks for like few details on what's the project, what's the current state, existing code base on say the A100, and there's a quick turnaround time on that. So once the request or the allocation is granted, so you can try out porting your applications on these systems. Again, we have in-house experts and our staff who can help you to leverage the systems for your use cases. And yeah, that's all I have. Thank you so much.
Do we have questions for Murali?
Thank you. What is the potential for higher levels of precision of this architecture? Is it a choice or is there a fundamental limit?
Yes, so currently there's mostly they're focused on half precision and lower at this point, but again, the key challenge when you talk about, especially with the HPC, is support for a larger precision. But yeah, there's some work going on that front.
Very nice talk. Thank you so much. On page 36.
You mean 36?
Page 36. Is that for training or inference?
Was it training?
Okay. Thank you.
Hello. Firstly, thank you for the talk. You mentioned that compilation of software, porting software over can take some time for these different systems. What is an average compilation time for, let's say, 1,000 line program?
So again, it depends on the model as such, but we have seen some examples where the compilation take like all the way from, like, say, a few minutes to a few hours. So that's the kind of range that we see. But again, it depends all on the model as such. Like if the model is pretty huge or massive model, so I'm talking in terms of the AI model here. So we have seen the compilation can take a few hours.
Any more questions?
Sorry, page 42. So this 10 times speed up from 1.17 to 1.18 looks very interesting. Can you elaborate a little bit on?
I didn't get your question, sorry. Okay. So I mean for the Polaris one?
Sorry.
So we are.
Let me repeat my question, if I may.
Yes, please repeat.
If you see the fourth bullet point, you have SN30 performance similar to 4A100
Yes.
on 1.17 release, and then
Yes,
you have
so-
optimized on 1.18.
So for the 1.17, so that was a preliminary implementation order. So you're seeing an equivalent performance on 4A100s. But again, with the next release, like 1.18, so we had more optimizations in the software stack, the Samba flow and the runtime, and that helped to increase the throughput much larger
I see.
numbers.
So that's the Samba Nova thing,
Yes.
not the Gen SLM or other.
Yeah, the throughput of the GenSLM on SN30.
I see. So the workload stays the same.
Yes.
But
Workload is the same with the new or the next software release.
do you know what kind of optimization they did, particular for this workload or in general?
So the source for the improvement comes from there's some optimizations happening in the compiler phase as well, and again better fine tuning of different parameters.
Figure out how to place those computations on the tiles.
That's pretty challenging.
Tricky pattern.
Yes.
Thank you.
Yes.
I think I saw some more hands on the other side. Are there any still questions? We have time for questions.
Okay. So I wanted to have a quick before a lunch break. So.
Thank you. A quick question. Can you train in one system and then do inference in another system? Is that something that's straightforward or no?
It's not straightforward at this point, but again, that's something we are working on that. It's not straightforward, like we are working with like how that can be supported. So, for example, the Grok system, I know it's an inference engine that supports you can take any model in Onyx format and then you can run them, use those for the inference jobs.
Beside ALCF, who else are doing AI testbed, and have you compared your results with theirs?
So within ALCF?
Outside ALCF.
Okay. So I know there are some deployments in other facilities as such, but I'm not sure if they have these variety of systems at one place. So they have like maybe one or two accelerators. So the AI testbed is like working on having more number of testbeds with different characteristics, which are kind of promising on that front.
If no more questions,
Thank you.
let's thank the speaker again.
Thank you.